All right, so again, before we go and look at some examples, we can talk about a couple of last properties of continuity, because we're going to start to see functions that are not so basic or not just our common functions that we've seen so far. We're going to start to combine functions together, and things are going to start to get a little bit more complicated in this course. So, here's a couple of properties that are going to help us as we combine functions together. Let's start out by assuming that we have two functions. If f and g are two functions, they're both continuous at a point A. Okay, or you could even talk about on an interval. That's fine too. I'll put it this way. Then so is, in other words, then f then the combination somehow is also continuous, uh, either at a or on the interval, depending on which one you're talking about. Then so is f plus g. In other words, f plus g is also continuous at a if f and g both are individually continuous at a. F minus g is also continuous at a. F times g is also continuous at a. F divided by g is also continuous at a, but with division you do just got to be a little bit careful with this one. This kind of has an assumption in it, assuming that g of a is not equal to 0, because remember, you're trying to plug in that value of a. Well, you can't divide by 0, so assuming that g of a is not equal to 0, and that we don't have any of those problems, then all four of these are continuous at a if f and g both are individually continuous at a. Okay, I'm going to throw in one last one. F and G are functions. When we talk about functions, we have one other operation, not just addition, subtraction, multiplication, and division. We have a fifth operation that only applies to functions. You've seen this before. This is a composition, f of g, or another way to write this is to say, so f of g of x, another way to write that is f of g of x, like this. And so when you compose functions, you also kind of keep the same intervals of continuity that the original functions had to begin with. So just some properties as we start to look at some different examples about how to be able to tell where a function, even a more complicated function, where a function is continuous and where is it discontinuous. Okay, so I said earlier that there are many functions that are continuous on their domain. In other words, if you can find the domain of a function, then you can find where that function is continuous. Okay, this includes a lot of different functions that you've seen before. For example, polynomials, any kind of polynomial. The domain is all real numbers. Polynomials are continuous everywhere. Okay, rational functions. The domain of a rational function is not all real numbers. In fact, we just saw one of those earlier. But whatever the domain of a rational function is, that is also where that function is continuous. The same thing is true for exponential functions, for logarithmic functions, for trig functions, for inverse trig functions. Even for others, for roots, okay, square roots, cube roots, other kinds of roots. So I would say for most of the functions that we know about, unless that function is somehow a piecewise function in and of itself, the functions that we've typically seen in past courses are going to be continuous on their domain. All right, so here's an example where we can talk about where is a function discontinuous and where is it continuous. And I mentioned that we are going to start combining together the functions that you know about. So here's what our f of x is going to look like. We're going to have something like e to the sine of x divided by 2 plus the cosine of pi x. And the question I could ask you is, does this graph have, or does this function have any points of discontinuity? Is there anywhere where this function is discontinuous? And really, kind of the flip side of that, where is this function continuous? Okay, so see if you can kind of look at this and kind of piece this together based on what we know. And remember what I said earlier is that a lot of the functions that we know about are continuous on their domain. Okay, so let's take a look at this individually. The sine of x, the domain is all real numbers. A function that's e to the x, the domain of e to the x is also all real numbers. Okay, so do we have any issues with domain on the top? No, we don't. We don't have even numbered roots. We don't have logs. We don't have fractions on the top. At least we have one fraction as a whole, but we don't really have any of those problems on the top. Okay. All right. Let's look at the rest of it. The cosine of pi x. All right. The cosine. Remember, the domain of a cosine is all real numbers. You can plug in whatever you want. And the only place where this seems like there could be a problem is the fact that we have a fraction. So remember, with a fraction, you're not allowed to divide by 0. So we want to think about this. Is there anywhere where 2 plus the cosine of pi x, is it possible for that to equal 0? And if so, where does that happen? Okay, and actually what ends up being the case in this situation is that there's not anywhere where that happens. Remember, the cosine of pi x, no matter how complicated the inside part of that is, goes back and forth between -1 and 1. That's the range of that cosine function. So the smallest that the denominator can get is when you have 2 plus a -1, which is still a positive value on the bottom. It's not possible for this thing to equal 0. So where is this function continuous? F is continuous, we would say everywhere, or you could also say on the interval from -infinity up to infinity. Okay, let's go ahead and take a look at a type of example that's pretty common. We could definitely take a look at different functions and say, where are they continuous, where are they discontinuous, and that's all fine and good. Here's kind of a different type of an example. Let's say we start out with a function f of x equals, this is going to be a piecewise function, and so I'm going to write it like this, 1 minus x squared, and that's going to be the rule that we follow if x is less than or equal to 1, and then we're going to use the natural log of x if x is greater than 1. Okay, so by the way, you could start out by asking what's the domain of this function, but because the first piece of the piecewise function uses every value of x that is less than or equal to 1, and the second piece of the piecewise function uses every value of x that is greater than 1, the domain here is actually all real numbers. And we do got to be careful because we just said earlier that the natural log or logarithms, you got to be careful there because you're not allowed to plug in a negative value into the log. But we're only using that piece of the piecewise function when x is greater than 1, so there's really no concern about plugging in a negative value into that log. That's not really an issue here in this problem. So what's interesting about f of x here is that f is actually continuous everywhere. Now that's not necessarily obvious here, because remember, what does it mean to be continuous everywhere? Is that it's continuous on -infinity to +infinity. This seems a little bit weird because with a piecewise function, it seems like those two different pieces are going to be kind of split up. It seems like we would have some kind of a jump or a gap there in our graph. But that's not necessarily true in a piecewise function. Okay, if you think about a graph like this, here is a piecewise function that kind of looks like this. If you take 1 minus x squared, this is a parabola that opens down. Okay, and this point right here where it crosses the x-axis is actually the point 1 comma 0. Well, if you remember what the graph of a natural log function looks like, it looks like this one, and it kind of does one of these, and they actually both cross that same point. Now, the piecewise part of this function says you don't use the natural log graph when you're before 1. You only use that after 1. And then you only use the other piece, the quadratic piece, before 1. And so you actually get a graph that looks like this. And this is actually continuous Again, think about the informal definition. I said, could you graph the whole thing without picking up your pencil? And I could, if I knew where I was going. You could draw it kind of here and then get to that point and then keep on going. And so this graph is actually continuous everywhere. But how can we check that? How can we algebraically find that out rather than just by graphing this? Because sometimes graphs can be a little bit deceiving. Okay, so remember, we want to think about the endpoints is where we might have some issues. So the endpoints of the different pieces of your piecewise function, it's actually fairly straightforward. Just take your first piece of your piecewise function, and if x is less than or equal to 1, we're kind of talking about a left-hand limit there and saying x is getting really close to 1, but from the left. Okay, and so what happens if you plug in 1? Well, if you plug in 1 into that first piece in the piecewise function, what you actually end up getting is 1 minus 1 squared. You actually get 0. And then the question is, for the second function, do you also get the same output at that endpoint? At that point, we're talking about a right-hand limit, okay? But is the right-hand limit actually equal to the output value? Now, the output value comes from using the first piece because of the less than or equal to part. But if the right-hand limit is equal to the function value, then we still have the situation where this is continuous. And so you have the natural log of 1. If you plug that into the second piece, the natural log of 1 is actually also 0. What's happening here is that one piece is kind of creating this closed circle, and then the other piece of the piecewise function has an open circle that's starting right there and then continuing. And so this function is actually continuous everywhere. This is kind of a common example to use. So let's look at one example. Let's say we have this function that is a piecewise function, and you have a closed circle up here, and then down here you have a kind of the second piece of that piecewise function, and you have an open circle down here. Okay, and so question is, what happens at x equals 2? Okay, if I were to ask you, is f continuous everywhere? Okay, no, it's not. And think back to the questions we just had. Where is f discontinuous, and on what intervals is f continuous? By the way, for this function, at least with what this graph looks like, you would probably say that f is continuous everywhere except for at 2. And so you'd have an interval from negative infinity up to 2 using parentheses, and then from 2 up to positive infinity also. But f is discontinuous at 2, okay? And so if f is discontinuous, and sometimes I abbreviate and put a little disc at DISC for discontinuous, is discontinuous at x equals 2, then the question is it continuous from the left, or is it continuous from the right? Or it could be neither. If there was a hole there, it wouldn't be either. Or if those were both open circles, it would actually be neither. It's not continuous from the left, it's not continuous from the right. But in this case, when we think about if there is a closed circle, then it's going to be one of those two. It's either going to be continuous from the left, or it's going to be continuous from the right. So let's go to the definition up here. Is it the case that the limit as x goes to 2 from the left, is that equal to f of a? So look at what happens when you have the limit as x goes to 2 from the left. You kind of take points as you walk along, and you get close to that value that has the closed circle there. And so f here is continuous from the left. It's not continuous in general, but it's continuous from the left. Okay, and is f continuous from the right? Well, hopefully it's pretty clear that no, it's not. If you go from the right, you're talking about having points down in this right part, and you can talk about the limit there. That's fine. The limit would give you this open circle point, but that's not equal to f of a. And so you would actually get two different values. Like when you talk about the limit from the right, you'd get whatever this output is down here. We'll just call that y1. And then when you talk about f of a, that would give you this y2 value up here, and those are different outputs. So no, it's not continuous from the right, but it is continuous from the left. Okay, not quite as commonly talked about as talking about like limits from the left and from the right, but still something good to think about.